We're going to focus on the first derivative test today. The question that we're going to answer in this section is using the first derivative and everything we know about it, power rule, product rule, derivative of e functions. We're going to use the first derivative of a function to find local extrema. We'll talk about what that means in a second. And intervals of increasing and decreasing. All right, so first of all, let's take a look at this picture before we get into some samples. This is a picture of the original function. We don't care whether the original function is below or above the x-axis. That's not what we're really focusing on. We're focusing on the sign of the derivatives. All right, this means it has a positive derivative when the slope of the tangent lines is going up. So this is going to be a positive tangent line, positive. Okay, positive, positive, positive. So I'll use these little plus minus signs to indicate whether we're going up or down. Up until it gets to here. Some of you might recall that this is a horizontal tangency, very important location. That's called the critical point. So I'll put CP here. That's where the slope is 0. Sometimes it changes direction. Now we're going to have negative derivative, negative, negative, negative. Okay, it's going down. It's got a negative slope. All right, there's a bunch of different ways to tell. And up until it gets to here, this doesn't always happen, but here at the origin, it flattens out. It's actually a 0 slope there, another critical point. All right, so I'll just write m is equal to 0. But here it doesn't change direction. Once I go beyond that point, it's still negative, and that's okay. All right, up until I get to my third and final critical point, changes direction here, slope 0, and then it becomes positive for the rest of time, and it gets increasingly positive as we travel to the right. Okay, so every function tells a story from left to right. You have to read it from left to right. It goes up, flattens out, goes back down, flattens out again, but continues to go down in a negative direction until it changes signs for the last time. These signs right here you're going to become familiar with. This is going to be this pluses and minus and a minus and a plus is going to appear on what's called a sign chart in a few minutes. Okay? Extrema. Local extrema is really simple. This right here is a maximum because it's at the top. This right here is neither because it doesn't change signs. And this right here is called a local minimum. Okay? Local minimum, neither, local maximum. Top, bottom. That's it. Real simple. It's called local because this thing technically goes on forever and it doesn't really have an absolute or a global maximum or minimum, but we could talk locally, and that's what this picture is. That's it. Here's an example from the function without the picture, right? And once we go through the calculus here, we're going to have a pretty good understanding of what the picture will look like. We should, anyway. So, step 1, as always, take the derivative. Sometimes you'll have to use the power rule, product rule, quotient rule, natural log rules, e to the x, sine, cosine, right? So all those rules have to be stored in your brain. Okay, right now I'm just using the power rule real quick. I'll fly through this derivative. All right, and then we're going to talk about what to do next. What we have to do next is we need to set the derivative equal to 0 to find these locations or these x values, the critical points. That's real simple. It's going to become very instinctive. A lot of times, not always, a lot of times we're going to set derivatives equal to 0, solve for critical points. Let's take a look at this function here, or this equation rather. I don't like how this leading coefficient is 3, so I'm going to divide by 3. You can't always do this, but in this case I can, so that's awesome. We have x squared minus 2x minus 8 equals 0. Solve by factoring. All right, x times x is x squared, so we put the x's here. Factors of negative 8 that add up to negative 2. Minus 4 and positive 2. We set these equal to 0 individually. We get x equals 4 and x equals negative 2. Always label these things as your critical points. It doesn't mean that there's automatically a sign change there, though, right? Because one of these things could be a shelf like this. But we'll check the signs right now. What we're going to do is we're going to set up a f prime sign chart. Always label your sign charts because in the future, in another video, we're going to be setting up a f double prime sign chart for second derivatives. So label your sign chart, put your critical points on there. Boom. We have to check values here, here, and here to find out what the signs are at the sides of our curve here. All right, so what we're going to do is we're going to plug in, let's plug in -3 into our first derivative. For this, I don't care about what the number is. I just care about whether it's positive or negative. So I'm going to take it and I'm going to plug it into the factored form right here. Okay? If I plug a -3 into here, I get a negative number. If I plug a -3 into here, I also get a negative number. And we know that a negative times a negative is positive. Okay, that's the first interval taken care of. Next thing we're going to do is plug in something in between -2 and 4. Easiest thing to plug in, 0. I'm going to plug it into this one, because this is a 0, this is a 0, and this becomes a -4, so negative. I'm sorry, -24. But yeah, you can use the factored form when you're plugging in, or the standard form from the beginning. That's up to you, depends on what you're plugging into. A lot of times I plug into the factored form right here. Alright, so the last thing I'm going to plug in is a +5, because it's got to be within this interval right here. Okay, if I plug in 5 here, I get a positive. If I plug in 5 here, I get a positive. We all know that a positive times a positive is a positive. Good job. Okay, I have my signs. That means that this graph starts out by going up, and then it changes signs here. Then it starts to go down, and then it starts to go back up again. So it goes up, changes signs, goes back down, and then goes back up again, just like your typical cubic function. Nothing crazy, no shelves or anything like that. Really traditional. So here it's increasing, here it's decreasing, and here it's increasing again. For the sake of finishing the problem nicely, what we'll do is we will label this sign chart, and that's really the extent to which we need to solve this. I'm just going to put INC here for increasing. I'm going to put DEC here for decreasing. INC here for increasing. And then I'll just put, if it increases and then decreasing, this is a local max. For now, this is all we're expected to do, okay? Eventually, we'll need to use interval notation and stuff like that, but let's keep it simple. And then if it goes down and then comes back up, that's a local min. So maybe give yourselves a little bit more space on your sign chart than I did, so you can do all the labeling here like I'm doing in blue. Because this in blue right here is really the answer to this question, okay? And that's it. That's a typical polynomial function that has critical points and sometimes increasing, sometimes decreasing. All right, so when we go to do other functions, it becomes a little bit more challenging. We have a function here where we're going to need the product rule. All right, so step 1, take the derivative. The first one times the derivative of the second. The derivative of e to the x is e to the x. Plus the second times the derivative of the first. The derivative of x squared, 2x. Set it equal to 0 and solve for your critical points. Can't do anything unless I know what the critical points are, okay? This is a little weird to solve, but I do see some similarities between this term and this term, which means I can factor out a GCF, so this takes us back to algebra. I'm going to factor out a x e to the x, because this thing has an x e to the x, and this thing has an x e to the x. We're left with one of the x's here. We're left with a 2 here equals 0. I'm going to set each of these things equal to 0 by the zero product property. This guy right here, and this little guy right here. They each have to be set equal to 0 to find my critical points. Just like earlier, I set these two factors equal to 0. All right, so for this problem, we have x equals 0, e to the x equals 0, which never happens, and then x plus 2 equals 0. This one's never going to be true, so don't worry about this one, right? E to the x will never equal 0, so that's not going to give us a critical point. And you could write that down and explore why that's true on your own. So x equals 0 is a critical point, and x equals -2 is a critical point. We throw them onto an f prime sign chart, and that's where all of our information will come from. All right, so throw on -2, throw on 0, plug in pieces of the interval, right, for each one, -3. Again, I'm going to plug that right into here, which means I'm going to get a negative here, times e to the negative 3 is 1 over e to the 3. This is actually positive. So we have a negative times a positive times a negative, which is a positive. That's a little tricky. Take the time to pause the video and really talk about or write out what I did there. All right. Oops. Okay, so that's positive. If I plug in something here, -1. Keep the numbers easy what you plug in, please. All right, negative here, positive here, positive here. So a negative times a positive is a negative. Okay, last but not least, I'll plug in a number that's bigger than 0. Definitely just plug in 1. So I have a positive turns into a positive when we multiply. That's it. So we answer the question just like I did earlier. All right, I'll grab another color. And to answer the question, we just go label crazy on our sign chart here because that's where all the answers are. We start out by increasing. We start to decrease. And then we finish the curve by increasing again. Okay. This is going to be a local max because it goes up and then down. So that's like the top of a hill. And then down up, that's going to be a local min just because of the shape of the curve. And I don't even need the picture to answer that, right? I know this is going to be going whoop up at the top, and this is going to be at the bottom. All the answers are right here, okay? In the future, we'll do interval notation, and we'll sketch out the graph. But this one's kind of cool, x squared e to the x. All right, I don't always do this, but I sometimes throw these things into Desmos just to see what it looks like and to double check to see if I got the right answer. It should be increasing, decreasing, increasing. Let's take a look. Sure enough, yes it is. Increases, decreases, and increases. And so that right there is the picture of that function that required the product rule. Sometimes it's good to just double check to make sure you have, in this case, 2 critical points and some changing of directions. First derivative test, know how to use it, know what it means, and you need to know what types of questions it answers for us. That's it. Nice job. Keep it up.